Okay. Hello, welcome to week 9. How's it going? I'm Sam, and talking Gen Chem nuclear chemistry today. I think this should go quickly, but I say something like that every time, and then it never does. Um, so we'll see. I'll just do my best. I have looked over these, but I haven't really worked them out yet, so we're definitely going to be discovering this together. Um, and Most of chemistry, I guess just to talk about what makes this nuclear chemistry, most of chemistry is all about electrons. And electrons are involved here. Most chemistry is all about what the electrons do in relation to nuclei and how nuclei or nucleuses share electrons with each other. But with nuclear chemistry, we're talking about the nucleuses themselves, involving particles such as neutrons and protons, which in and of themselves are called nucleons, I believe. Double check that. So, speaking of this first question, nuclide notation, what we have here, nuclide notation, is there's not a Q, I believe. I don't think, well, I'll do X. So element X. X is the element's name. Z is the element's, there's kind of two good ways to think about it, three good ways to think about it. Z is the number of protons in the nucleus. So number of protons. Z also, since each proton has a charge of 1, Z is also the charge, by the way. It's the positive charge of that nucleus. So also, that this might be superfluous in a way. Number of protons is definitely the best thing to think about Z. So in the case of carbon, that's 6. But it's also the positive charge, because each proton has a +1 charge. And the third way to think about it, I said there were three. The third way is that Z is basically what defines the letter. If you were to mess around with the number of protons and make that a 7, all of a sudden that becomes an N. If you messed around with the number of protons and made that an 8, now it's an O, etc., etc. So Z also, I'll do in that same color, also defines X. And X is the letter name. Okay, so then we just have that top corner where we have A, and A is the mass. Now, mass is the neutrons plus the protons, and each one is worth 1. So I just want to note that if you look at a periodic table and you see these molar masses, like iron is 55.845, that is similar but not what we're talking about exactly, because these numbers that you see on a more conventional periodic table here are the average masses of all the isotopes adjusted for their natural abundance. What that means, essentially is if you actually had a mole of this stuff, the average mole of it would weigh that much because you would have a mixture of various isotopes. A mole is 6.022 times 10 to the 23rd, or 6, and then like basically 23 zeros. A mole is a lot of atoms, so you're going to have some variety mixed in your mole. So that is different than nuclide notation here, because with nuclide notation, we're just talking about a single atom at a time. You know, or a single particle, if for some reason it's not appropriate to call the thing we're talking about an atom in any scenario here, but we're talking about just one at a time. Therefore, it's kind of cluttered around here, so maybe I'll just write this over here. Since we're talking about one particle. It is an atom. I'm going to say atom. Well, really, we're not talking about the full atom, are we? We're talking about one nucleus at a time. Z and A are integers. Therefore, all that wind up for this point. Z and A are never, in our nuclide notation, are never going to be these average numbers like that. They're going to be integers. And the other thing is that since Z is the number of protons, and A is the mass, which is neutrons plus protons, if you know one or the other, you can typically figure out the other. So if we were told the number of protons, we would just, the number of neutrons, we would just add that to the protons to get the mass. So that is how this works. All right, so let's do these first ones. I'll make all this stuff small for us. Hope it catches all that. Okay. I missed this little bit down here, but go join your friends. Okay. So oxygen 14. I mean, we can really quickly do all of these by saying, since we're given the names, we essentially know what Z has to be. Because Z is the number of protons. The number of protons is what identifies the atom, or the nucleus of the atom. Tantalum. Off the top of my head, I want to say that's Ta. We'll find out. I'm pretty sure francium is Fr. Let's see if I got all those correct. I have to look at the periodic table anyway here, because I need to know the atomic numbers of each. So speaking of atomic numbers, Z for any of these is just this number. Whatever number that element is, like carbon is number 6, calcium's number 20, niobium is number 41. Oh yeah, let's find the one that we need to find here. Tantalum. Oh nice, I got it right. I kind of guessed, but apparently I guessed it correctly. Tantalum's right there. Number 73. So that's its number of protons. So I guess I'm going to do, well, I'll do that tantalum in a sec. So that's its number of protons. 73. Oxygen is 8 right here. Copper, 29 right here. You know what, though? I wrote those so close to each other that you kind of can't tell what's an A and what's a Z. So let me do these one at a time. Maybe I'll do them in different colors, too. Oxygen can be purple. So oxygen is, its Z by definition is 8 protons. And we're told it weighs 14 right here, so kaboom. There you go. Oxygen 14, not a very common type of oxygen, I'm sure, but if you had a mole of oxygen, a tiny bit would be that, and that would be part of the reason that the actual mass of a mole of oxygen, the average mass is going to be a little bit less than 16, right? Right? It's 5.999, not 16. Because some of them might be oxygen 14 or oxygen 15. Copper will obviously do in, is there an even more coppery copper color? Orange is coppery enough. Okay. We found that as 29, 70. I mean, now it's super easy. Tantalum will give this cool light blue color. So Ta for tantalum, it was element 73, and we are told in the name that the mass is 175. And then francium, I know is right here. Francium is the most explosive and unstable of those alkali earth metals over there in the first group of the periodic table. It's 87. So francium, let's give francium, I guess this dark blue seems right for francium. Okay. And element 87, 87 protons, and its total mass is 217. So just for fun, I'm going to do a little bonus question on this question and just show you that the number of neutrons is really easy for each one of these, right? So we have 8 protons in oxygen. The total mass is 14. So there must be, in this one, 6 neutrons, right? Because whatever that total mass, A, up there is, that's protons plus neutrons. So with copper, we have 29 protons. Oops. So that means we must have 41 neutrons, because 29 plus 41 equals 70. And over here with our francium, we have 89 protons. So we must have 30, by which I mean 100 and 30, this one a different color, 130 neutrons, etc. And then for tantalum, we have 73, so that must be 102 neutrons. This question did not ask us to find the number of neutrons, but it's that simple, and other questions quite likely will ask you to find that. So that's the thinking. This is that simple. That's nuclide notation. And again, what differentiates this week nuclear chemistry stuff is that we're actually looking inside the nucleus, whereas typically in most of general chemistry and organic chemistry and biochemistry, nuclei are static. They just remain the same. It's what the electrons do that defines a chemical reaction. Um, so this is finally peeling uh, off the banana peel, I guess. Apparently, I don't know. That's not a great metaphor. Maybe let's make it an orange, because at least that's round. Yeah. So we've been studying the orange peel, which is electrons, and now we're peeling that off and looking inside the orange. I don't know. If I edit this video, I'll probably edit out that metaphor, but also I now totally want an orange. But I'm going to hold off. I'm going to reward myself after this with an orange. So there was nuclide notation using the periodic table. So here's the cool thing, the band of stability, figure 21.2 in the book. We see that there's a ratio of protons to neutrons that influences how stable an isotope or a particular version of a nucleus might be. And let's note that if you're outside of this green blob here, and it looks like a blob, but if you zoom in, this is actually very quantified, right? It's very distinct bands. It's going up in integers, right? This is integers, it's quantities, it's a number of protons. You can't have 2.4 protons, at least not at this level of quantum zoom. Maybe there's some deeper physics that I don't know about where you can have fractions of protons, but this chart and this concept and this level of scientific theory, we have you either have 0, 1, 2, 3, 4, 5, 6 protons, etc., up to 120 on this chart. Similarly, that integers of neutrons going up to 180. And if you try to have a certain number of protons and neutrons that's outside of the green band here, then that nucleus will essentially just not work. It'll instantly fall apart or not happen, or those particles will be more stable in some other configuration that does fall within this green band. So that's one thing about this chart, is that you're essentially not in nature going to find combinations of protons and neutrons that don't lie within this band of stability, because if they start to, like let's say you somehow got 40 protons and 110 neutrons together, and you tried to force them to hang out here, they would split up and probably break into a couple of these and this, and then decay, and etc. So that's the next part, by the way. If you are in the green band, you being a nucleus, then you're stable, but you're not that stable because you'll keep falling apart until you become a non-radioactive thing. So anything that's on this blue line is basically a happy nucleus that's not going to fall apart. And if you're on the green, you'll exist for some time, but eventually fall apart until you become something on the blue line. And one interesting thing to note, when you have a small number of protons and a small number of neutrons, then it's basically one-to-one that makes you stable. Again, you're a nucleus in this case. So if you have a one-to-one ratio of protons and neutrons, which would, look, it looks like this one-to-one thing goes up until 18 right here, right? Because here's 20. We can count it more in depth. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Uh, and 18, so that's going up by proton. 18 protons is argon. So this like actually super makes sense. So essentially, up until argon, or up until the point where we're only talking about S shells and P shells, up until argon, a one-to-one ratio of protons to neutrons is stable, right? That's this black line, the one-to-one ratio of protons to neutrons, right? Like out here on this black line, it's 90 and 90, 110 and 110. So that's pretty interesting up until argon. But once you start adding other shells, then things change. And we can see that you need more and more neutrons to be stable. Okay, so that's what's up. This is really cool, I think, and kind of like part of the defining nature of physical reality, apparently, according to our scientific theories. So pretty cool stuff right here. So let's see what lies within the band of stability. I mean, if any of these actually exist, once again, if any of these things actually exist, they must. But we can posit things that may or may not exist. So let's see. Chlorine 37. Let's start there. So chlorine, I think, is 39. No, that's its typical mass. It's number 17. So chlorine is number 17. So this is when we found neutrons on the previous problem. That's exactly what we're going to do now. So chlorine 37 must have 17 protons, and it must have 20 neutrons, because the number of neutrons is simply the difference, and neutrons is the difference between the mass and the protons. It's that simple. So now we're going to look over here and just find 17 and 20. We have our x-axis is our z, our y-axis is our neutrons, and by z in this case we mean protons, and positive charge, incidentally. So I feel like this is going to be within the band of stability, but it's definitely not in the non-radioactive part. So here's 10. So 10, here's 11, 12, 13. Oh, except for, sorry, each one of those was a count too. So 10, 11, 12, 13, 14, 15, 16, 17. So there's 17 right there. And honestly, I could probably eyeball this, but I'm just being meticulous so you don't have to. Or so that you'll also be meticulous or something. So 17 and 20. Actually, it is a stable isotope apparently because it's right there on the blue line. Looks like that works. So 17 and 20, that one looks good. So that's a solid yes. Not only does chlorine 37 appear in the band of stability, which is the big green thing, it's even looks like non-radioactive. So good for it. Good job. And what does radioactive even mean? Don't worry. We're going to talk about that. So calcium 40. Calcium is element number 20. Calcium 40 sounds like 1-to-1, but it's a little big to perfectly be on there. So this will be interesting. So, sorry, this zooming's not going quite how I want. There we go. Calcium 40. We'll do calcium in orange. Calcium, Z is 20, that's 40. Therefore, it's going to have 20 protons and 20 neutrons. So that's 1 to 1. So it's right here on the line. So it is radioactive, right? Let's zoom in here. And I guess I'm going to be consistent. I did that other one with the green marker, the chlorine. So there's that. 2020 is right there, that orange dot. It is not on the blue line. So calcium 40 that has 20 protons and 20 neutrons. Calcium 40 would be radioactive. We could speculate about what it would do, if it would become some sort of chlorine over here or what. And I think we are going to speculate about such things, but for now we're just determining if it does or doesn't lie within the band of stability. So this one is also a yes, but this one's radioactive, and chlorine was not radioactive. Okay, how about bismuth? 240. Let's find bismuth. Bismuth's right here, 83. Okay. Oh, and we're looking for bismuth 204. Bismuth blue, I suppose. So, got our bismuth. Its number of protons is 83. Talking bismuth 204. So 204 minus 83 is going to be 121 neutrons. With the 83 protons, I'm going to double check myself. I mean, yeah, that's obviously 204. 204 total particles. Nucleons, right? Your protons and neutrons together are called nucleons. So now we're going to find x-axis 83. I mean, it's going to be approximately right here. I don't know why sometimes that many. And then 121. I mean, that's going to be like right about here. It looks like, well, here's 121. Let me actually zoom out. 83. Oh, I think we're definitely good. And this would actually be a good time. Let's use a line here. So I can actually, there we go. I'm holding down shift, so it's going at distinct angles. So I want to point out that this is only valid if you make sure that the line is perpendicular to the x-axis, right? So right here at 83, I just drew that line. And let's do another line on the y-axis. Let's do it in that color for fun. Line, shape, line, draw a. Again, I'm holding shift. If I don't hold shift, it'll let me be wonky with my angle. So you hold shift. And I mean, maybe a different program, it's a different button, but here it's that. Okay, so now we can move this. Come on. That's way. There it is. There it is. Oh, this is hard to move this line for some. Okay. 121 would be about there. So yeah, I think we're safe. My lines might be slightly off, but we're clearly right in that band of stability. Are we? I think we're still radioactive, right? Because where they intersect does not appear to be on a blue thing, but I kind of eyeballed those. Let's call it a yes, and we're going to say that that's probably radioactive. We could get a little more meticulous, but I think you get the concept is the point right now. Let's just finish all of these, though. Thank you. And so iron, 56. And iron is element 26. So obviously it's got 26 protons, and it must have 30 neutrons. And I guess now that I drew these lines, let's just use them. So we're going to move this down to 30. Well, I guess we didn't. There's already a line on 30, but there it is again. And 26. So again, if you want to be really meticulous, as I did with the chlorine example, you could count out every time this moves, and that should basically work, I think. But I'm just going to continue to be happy with sort of eyeballing it. Wait, it's 26? I'm looking for, yeah. 26 would be basically just past halfway in between you and you, 20, 25, 26, right about there. And they super intersect right in that band. And honestly, probably right on that. So this is probably a very stable, non-radioactive isotope of iron. And this figure, by the way, this band of stability thing, geez, are we going to get any no's? I hope we get some no's here. I'm going to really doubt what I'm doing. Right? Seems a little too simple. But anyway, this band of stability, experimentally determined. Like, we build our theory on the experiments, not the other way around. So somebody didn't just come up with the band of stability, the results kept suggesting it, and somebody came up with the band of stability thing here as an explanation for the results. And when I say somebody, I'm sure I'm talking about multiple somebodies. Okay, we have lead, 82. No, we had bismuth earlier, 83. Lead and bismuth, probably frequently associated. All right, so lead is 82. Nice, we actually have two different isotopes of lead coming up here. So that'll be interesting. Smaller. Lead, I'll do in black. Well, lead's really more to silver, isn't it? So let's do lead like this. Lead, 82 protons. We have 206 total mass. 206 minus 82 is going to be 124 neutrons. And once again, we had 82 protons. So, I mean, now this is just too easy, right? 82 is, well, I guess it's right next to where our bismuth was. Basically there. And 124, I guess that previous one was 121. So once again, we're going to be quite close to bismuth. So this is probably going to be in it. Well, let's confirm it. 124 this time? Definitely. Super stable. This, in fact, look, this is great because we're right on the non-radioactive blue. So this is actually happy lead right here. Lead 206 is in the band and it's non-radioactive. With iron, I was being a little sloppy. I didn't really tell, but this is obviously right on it. So if we have the exact same thing, except for this time, led to 11. So this time, 129. I mean, I probably could have done that without laying it out, but now we have 129. So this will probably lay within the band still, but it might be radioactive. Let's see, 129. Actually, that appears. Oh, wait. That's funny. I got my blue line and their blue line confused for a sec. But so in the band, but it's radioactive now, which totally makes sense. So if you have lead 211, it's going to do some radioactive stuff and try to become something stable. Maybe lead 206, maybe, but maybe something else. But once again, we have a yes, radioactive. And radon I'm pretty sure that's radon, not radium. Radon 86. Pardon me. And by the way, this is kind of interesting because, like, once we get above bismuth, notice that no longer what I started out talking, what I started this video out with talking about, what I started this video out with talk. Oh man, why is that such a hard sentence? The first thing I talked about during this video was the fact that these average numbers are not what we're talking about with these nuclide masses, right? This is the average mass. If you take the isotopes adjusted for actual natural abundance and you had a mole of it, how much would it weigh? But note that once we get bigger than bismuth, which we're going to go look at that band of stability. It's like once you get bigger than bismuth, it's just the theoretical mass numbers now. For the normal isotope is basically what they're showing us, or probably for the most stable isotope is what they're showing us. Oh, there you go. It actually says it right here. So for elements with no stable isotopes, the mass number of the isotope with the longest half-life is in parentheses. So that's really interesting. That's 83. That's like the biggest you can be if you're a nucleus and be stable is 83. If you're bigger than that, maybe you can linger for a few minutes, a few seconds, maybe you can linger for years. But eventually you will fall apart until you become something of that size. And let's just note that the last thing, it's right here, it's that bismuth. It's the end of this right here at 83, where I originally drew that. That's the last time we have a non-radioactive thing. After that, you can have stable enough, but not stable enough to make it onto the periodic table with any reliability. So that's pretty interesting. 83 is this, apparently it's a size limit of protons for stability in our current universe. Really cool. Okay, so radon, by the way, falls into that category. Um, that's not actually the question, though. I just think that's really interesting to note. And that's a really important take home, I believe, with all of this. In a sense, what is radioactivity? It's when you get too big for your britches and you have to fall apart. It's when you're bigger than 83 protons, and that's not tenable long term. So speaking of bigger than 83 protons, radon is 86. And we're told that this is 222. So our number of neutrons is going to be, it's going to become a 1, 1, and that's going to become, oops, 12, so that's become a 6, and that's an 11, becomes a 3, and a 1. Yeah, that looks right. Okay, so 136 neutrons. And I mean, like, use a calculator, by the way, for that kind of stuff, but also don't use a calculator, because don't you want to be able to add and subtract? Use it or lose it, yo. Basic arithmetic atrophy. Avoid. Avoid arithmetic atrophy and alliteration. Anyway, let's see if 86, right about there, and 136 on this band. It looks like we still are. We're still in the band. Okay, right there's our intersection. But we are radioactive for sure. And of course, radon is famously radioactive, so that makes sense. And then carbon 14. So these were all yeses. All of them. These. Not all of them lie on the non-radioactive line, but all of them lie within the green. So I don't know if the band of stability, I guess maybe I was wrong earlier when I said the band of stability was the big green thing. Maybe they do just mean the blue thing. Uh, Yeah, maybe the blue thing is the band. I feel like they don't make it very clear, and they didn't in the text from when I just read it, but I did skim it pretty fast, so maybe they did. Um, Everything else that has been discussed in this video, I think, is correct. I just may have used the vocab wrong in distinguishing the central blue thing from the green thing in terms of what per se is the band. But carbon 14 is 6 and 14. Wait, so 6 is more like here. Oh, except for, sorry, carbon 14, of course, is going to have 8 neutrons. So 8 is like right here. So we would be at 6 and 8. Yeah, right about there. So we're within the green, but carbon 14 is not. Normally carbon 12 is the stable thing. So carbon 14 would be radioactive. So, okay, awesome. So, yes, but that's radio. So essentially we had like lead 206 and chlorine 37 were not radioactive, but pretty much oh, and I think iron was maybe, it was, I don't remember. I could find out, but let's move on. But everything else was radioactive. So everything else was in the green, but not on the blue. But a few things were on the blue. So, okay. This is kind of fun because we have these question marks. We just have to sort of solve these algebraically. And here are the things we can do. These are like the moves we're allowed to make. If this were some sort of board game or something, these are the permitted moves. Is look, every time we can do an alpha particle, which decreases the total mass, the A by 4, and decreases the charge or the number of protons, Z by 2, or just increase Z by 1 with beta decay. Uh, this will be irrelevant to our purposes unless we have something denoted with an asterisk. That would mean that it was this excited. Excited is that asterisk. Nuclear state becomes non-excited. That's not going to be pertinent to any of these, I think. We can decrease the proton number by 1 when a proton becomes a neutron. But it doesn't change the total mass. But you'll notice in this drawing, the protons are these green ones. And a proton can lose its positivity and it's a neutron. Something like that. Probably the quantum physics of that situation can be more accurately expressed. But as far as what we're doing with this nuclear chemistry, that's what's happening. And electron capture is a version of the same thing, except for instead of losing a positive, it gains a negative. And once again, a green plusy proton has now become a neutral. I guess that's my neutral thing. Look, for neutral, I was going for a yin-yang because I feel like that's kind of like about neutrality, kind of. I don't know. If you're a commenty person, tell me if that's a good symbol for neutral. That's what I was going for. Okay, but it just turned into an S. So, oh, we can also add a few other things, by the way. So this is how stuff could lose. These are types of radiation that could happen. Oh, but I think this is actually more important for this one, now that I think about it. This is sort of about the same thing, but I guess this is actually what we should use. All of those statements were describing a type of decay, but we're simply going to use these symbols and then figure out where it goes from there. So let me actually screenshot these, bring it over to this question. Let's be on top of that, and so be it. So this is interesting because right off the bat, check this out. 4,2He, we end up with 2 alpha particles, right? So we're starting out with lithium-7, and it ends up as 2 alpha particles. And the thing is, we need to balance all of our A and all of our z for both sides. So as it stands here for A, our left side A, sorry to say A so many times, but for question A, the total mass, which is designated by a capital A, that we see right now is 7. We're going to add something to it. And the total mass that we have here is 2 times 4, so that's 8. So we clearly need to add 1A to that side in this question mark. And the Z over here is 3, and the Z over here is 2 times 2. So let's say this is A on the left, A on the right. Z on the left, on the right. And we have 3, and we end up with 2 times 2, and that's 4, so clearly we added 1. So how do we add 1 and 1? It's with a proton. I guess it's up to you if you want to designate it as a capital H, which stands for the nucleus of a hydrogen. That's how I'm going to do it, because it's just more consistent with a lot of other chemistry nomenclature. But, you know, you do you if you'd rather write it with a P. Totally cool with me. I'm not going to sit here silently judging you. No, I'm going to do it out loud. I'm totally kidding. Okay. So, our first question mark, I think we can safely say, is it still this one? For this, it's 7, 3, or it's lithium 7 plus a proton, and then that'll basically give us some sort of like high energy transition state that is lithium. Sorry, it's not even lithium. It's number 4, which is beryllium. Beryllium 8. We're going to have this transition state where we turned our lithium briefly into beryllium, but then that beryllium transition state will fall apart into the 2 alpha particles, or helium nuclei. Okay, let's do B. Carbon 14, the radioactive one from the previous problem. So our A on the left is 14. Our Z on the left is 6. Which, right as I mean, not as I say. Oh, so our mass is already taken care of. So whatever our question mark here is, we don't want it to change the mass. What does happen is we have an increase in the Z. So which of our particles increases a Z? It's a positron. So we're gaining a positron, which is like a weird like antimatter electron or something. Cool like that. I don't really know quantum physics that good yet. I hope to. I hope someday to know quantum physics better than I know it right now and know if I'm speaking correct. But as far as nuclear chemistry goes, that's what we need, right? Um, oh, except for not. Wait, let me think about that for a sec. That is wrong because it's on the wrong side. That's so, okay, that's right. So by the way, the thing that I just wrote would have been correct if the question mark here on B, if the question mark were on the right side, right here, then it would be gaining a positron, and that would be correct. But let's note that it's not actually plus a positive that we're talking about. The thing that is being emitted is coming off. Something's coming off of it. So we're losing something. So what we're actually losing is a beta particle. We're losing a negative. We're losing an electron, basically. So that's what it is. It's actually plus a beta particle. It had a charge of 6, and it lost some of its negativity. So what does that really mean? It is like a proton. Here is all plusy. And then you have an electron here that's all minus E. And notice how I drew the electron on top of the proton, because when they're together like that, they are a neutron. An electron glued onto a proton is a neutron. So if the neutron loses that electron, now it's no longer a neutron, now it's a proton. That's what's just happened here in B. We had, use a different color, we had 6 protons. That proton lost its, sorry, yes, 6 protons and therefore 8 neutrons. One of those, let's say this was number 8. Number 8 lost its electron and therefore became another proton, number 7. So that's what just happened there, and that was a beta particle, beta emission. Okay, let's check out this next one. Number C, let's do in this magenta color for fun. So we have number C, you know what I'm talking about. Okay. Also, you probably can't hear it, but my cat is snoring on the chair behind me. It's very adorable. Okay, so over here we have 27 and 4. This is our A's for the right side. 27 and 4. And our Z's for the right side? Ah, man, let me clean this up a bit. First off, actually, there we go. So 27 and 4, and our Z on the right side, we have 13 and 2. There's our 27 and 4, 13 and 2. So on the right, by which I said right several times. I meant left when I said right. On the left side, I guess I'm going to claim that I said right because it's the reactant side and they both start with R, but yeah. So on the left side, we have a total mass of 31 and a total number of protons or total charge of 15. And on the right side, we have our question mark, but we have a neutron. It literally just like lost a neutron, apparently. Oh, while gaining an alpha particle. I see. So the question then, we basically know that it has to be 15. This part is kind of set in stone because this is a 0. So we need to end up with 15 on the right side. And we need a total of 31, and we have 1 over here already. Kind of organizing this weird, I apologize. We already have 1, so it must be plus a 30. So whatever question mark is, it must be 30. 30, 15 has to be question mark. And by definition, 15, if it has 15 protons, it's phosphorus. So this is got to be phosphorus 30. So that complete equation, to make it not look terrible, for C, write it better, we have aluminum 27 plus an alpha particle, which is a helium nucleus, becomes phosphorus 30 plus a neutron. There's C. All right, one more of these, and then we'll keep doing more of stuff. And how long have I been going? There we go. I'm going 50 minutes, it looks like. See, I asked that, and presuming I didn't edit this video at all, which I almost certainly won't, you can just see how long I've been gone. But I had to look for it. Then I also saw it. Okay, anyway. CM. I do not know what that is off the top of my head. I think SR is strontium. But it looks like on our left side, I think this might be a better way to organize it. Our A and our Z, our total on, this is easy because the total on the left side is 250 and the total on of the Z on the left side is 96. And then on the right side, it looks like we have 98 and 4 times 1. So right there, the mass for those two, the strontium and the neutron, is 102. 4 plus 98. And the Z for those two, the neutron does not bring any Z, so 4 times 0 is 0, so it's just still 38. But let's note that over here we have 96, so that's a big difference. Let's also note that right here we have 250. And here so this is going to probably represent a fission reaction where instead of I'm looking to see if any of the random refuse about here would be good for exemplifying. But instead of what I'll do is just use my hands. So pretend that my fists together were a large radioactive nucleus. They could shoot off little parts. Like imagine I'm like losing the tip of my finger or something on some of these, which I'm glad I'm not actually doing. That would just be radioactive emission or slow radioactive decay. But fission would be if it just cracked into two pieces. So instead of other types of decay that we've been sort of looking at, you have a nucleus that shoots off tiny parts of itself, or maybe gains tiny things, and morphs and transforms that way. Whereas with fission, it's two smaller, sorry, it's one big thing that breaks up into two medium things. Instead of a big thing shooting off small things, the one big thing becomes two medium things. That's fission. A fissure, a break, a cleavage, nuclear fission. Um, and then fusion's the opposite. Fusion is when two medium things glue together. So in this case, it looks like we're looking at a fission of some sort. Because on our right side, the total we have before we add in whatever the question mark is, that's the A and the Z. So the question mark must account for whatever this difference is. So the difference between 250 and 102 is 148. And the difference between 96 and 38, 96 minus 8 brings us to 88, minus 30 must be 58. So we're going to get, for D here, write it out, this element Cm, which I'm going to go look up what that is before I say it. Maybe Californium? Maybe that's Californium. It's going to result in this question mark molecule, which I'm going to go look up also in a sec, plus some strontium 98 and neutron. Okay, so we're going to look at what Cm is. Curium, not californium. Where's californium CF right here? They're close. This is curium though. And our curium, I think it was 58. Is that right? 58. Cerium, CE, 58. Was it 58? Yeah. Okay. CE, and just that's curium, named after Marie Curie, and cerium. And I'm pretty sure SR was strontium. Let's go double check that too. Strontium, SR. There it is. Strontium. Okay, strontium here under calcium. This row right here. Radium down there. Cool. So that was 14. So we had several different things going on. Let's talk about technetium 99. Okay. So apparently we're making technetium 99. So let's just start right off the bat by finding technetium. Technetium 43. And look, you can tell it's not stable. Oh, this is interesting. It's actually inside this, it's under 83. So I did not notice. This is at least one example of a radioactive thing that is less than 83 because there's not a good stable isotope, right? So they're giving us the mass as a theoretical quantity like that. There we go. Technetium 99 is prepared from molybdenum 98. Molybdenum. I should like, if I'm going to screenshot it, I should zoom in. I guess they're apparently right next to each other, so I could have just done that in one, but I was not thinking ahead. Okay, and combines with a neutron. So we've got some version of technetium combining with a neutron. Give me that. N in this case is a neutron. And that is an N, not a U. I feel like that looks like so many different possible letters. Let me just make that more obviously. N, neutron. So it combines with a neutron to give molybdenum 99. Okay, so it's like a multi-step reaction. So part one, technetium and neutron give us molybdenum 99. Oh, yeah. Technetium's our ultimate goal. That technetium is not the subject of the sentence right here. Molybdenum 98 is the thing that combines. That makes so much more sense. Molybdenum 98. And by the way, like if you have written MO, that implicitly is 42. So you could skip the Z, but let's just not for now. But I do think it's legitimate to skip the Z at a certain point. And that's an unstable isotope that emits a beta particle. So once again, a beta particle is an E minus 1. It's an electron. It's an electron that came off of a neutron, essentially. So this then, reaction 2, is that this emits a beta particle to yield an excited form of technetium. So that's when our 42 goes up to 43. This is our Z here, right? So since we lost a negative, 42, so this is really the Z now here, equals 42 minus negative 1. That's how it becomes 43, technetium. And it's already 99. But it says it is the excited form. Right, it's agitated. It's as illustrated here. It has an angry red line around it. It's excited. Ugh. It's so frustrated and anxious, and it really just wants to get rid of some energy. How does it do that? It is probably going to emit a gamma particle. That looks like it says Y ray. It says gamma ray. Gamma. Like, well, something like that. Alpha, beta, gamma. Then you got your like lowercase. Well, here's your capital delta. Lowercase delta. There you go. That's lowercase delta. Anyway, we're not talking about the Greek alphabet, and I only have a very wonky working knowledge of it as I encounter Greek letters here in science. But that's gamma, not Y. So gamma is what gets rid of the frustrated, anxious, excited energy of this excited state. So, oh, I didn't even realize I was answering this question. I was just keeping track of what it said, but apparently I'm just doing this question. Write the equations for each of these. So that's what I'm doing. So equation number 1 is molybdenum 98 plus a neutron becomes molybdenum 99. And then I'm just using that for the beginning of equation number 2. So we'll say equation number 1. Then equation number 2 is that the molybdenum releases a beta particle, creating the excited state of technetium. And then equation number 3, where our excited technetium 99 is the starting material, will release a gamma particle, which does not change anything about the A or the Z. What it changes is that our technetium 99 is now not excited. It's just normal. So yeah, that was that. And I guess with the gamma, since those are both zeros, let's just not even write them. Okay, so that's the three-part system of equations I just wrote there. So cool. We are coming up on the end of this, which is good because we're at an hour, but I'll totally finish this one off today. So which of the following nuclei is most likely to decay by positron emission? So first and foremost, let's go find chromium, manganese, and iron on the periodic table. We already looked at iron today. 30, 26. Chromium, oh, nice. They're all right in a row. Perfect. What's going on? You gonna let me paste it? Pasty. Okay. Here we go. All right. It like pasted it into it. That's fine. We can work with this. So first off, let's note that our number of protons for all of these, Z, so 24, 25, and 26. So I think what we're basically thinking here, we're going to look at that band of stability, whatever that was with the little green vibe going on. You know what I'm talking about. We're going to look at that and see who could get into the best spot on that by positron emission. So that's a crucial part of this question. What even is positron emission? So for one thing, emission means that it is sending it out. It is emitting it. It is releasing it. So it's a product. It's on the right side. Emission means that the positron is a product that's on the right side of our equation. And a positron is like an antimatter electron. It's like an electron that weighs nothing, but instead of a normal electron having a negative charge, it has a positive charge. So which one of these is most likely, and whatever it is, its initial Z is going to lose a positive charge. So it's going to lose a negative. So it's Z. So if it were chromium, it would go from 24, its Z would go from 24 to 23 plus a positron, right? If it's manganese, then it's going to go from 25 to 24 plus a positron. I don't know what that is right there. Oh, it was a 1. I do know. Sorry. I got confused by my own squiggles. I don't think I have like great or terrible handwriting. Hopefully you agree with at least the second part of that. But even I was confused by that squiggle. Okay, and if it were iron, then we would be going from Z of 26 to 25. So which of those is most likely to happen? Well, now we have to assess the number of neutrons involved in order to get a good sense of that. So for chromium 53, the number of neutrons clearly is, sorry, I wrote that real small, 53 minus 24, which is going to be 29. So for chromium 53, we're going to look on the actual band of stability. We're going to look for, because right, this one was protons in the first place. So we're going to look for 24 and 29 and see if it would be good for it to lose a thing. So let's just start with that one. We'll do these one at a time. So 24 and 29. I guess I'll use my handy dandy. I should probably make this line a different color though, so I don't get confused with the. Where's my neutron line? There it is. I'm gonna make these lines more of a red so I don't get it confused with the one that's already in there. You probably had that idea already earlier in the video, but I didn't have it until just now. Okay, we were just talking about 24 and 29, I'm pretty sure. So that's like 25, and now I might need to get in there and get real meticulous, but oh, don't know what that was. 9. I mean, this looks like it's doing well. 24 and 29 is on the blue pretty much. I mean, maybe I'm one off. Like, I guess I could get 1, 2, 3, 4. Is that 24? No, that's 23. That must be, that's 20. 21, 22, 23. 24 is right here. I think we're right on the blue. Honestly, I kind of wish that this chart had unambiguous demarcations for every single one, because that'd be cool, but it doesn't. That said, I think our chromium 53 looks like it's all, basically it's already happy. We're not trying to change anything. Manganese 25, let's just make it clear that, so this is 29 neutrons and 24 protons, and it's online, not likely to decay at all. It's stable. Manganese 51 has 25 protons, so 51 minus 25 is 6 is 46, 26, sorry, 26 neutrons. So let's see how that looks. 26 neutrons, going to be more like here. Oh, this one's kind of interesting. This kind of makes, this could be the one. And 25. So yeah, like look at this. So it's not on the blue. So it would probably be into something changing. And what have we talked about? We said that here it is. Made it real small. But it's going to make it go to 24. So if it had a positron emission, then the number of protons would go down by 1. And would that make it, if this went down by 1, are we now in the blue? We're still not in the blue. So it is radioactive, but probably more like an alpha emission is probably more, it would probably more want to do an alpha emission to get in the blue. So probably it's not that one. So I hope it's our last one. Let's find out. With manganese, it's, yes, it's radioactive as manganese 51, but specifically positron emission is not likely because that would not get it onto that blue line. So how about iron 59? So that, once again, iron is 26, 59. So that means it's got 26 protons. And 59 minus 26 is 33. We've got 33 neutrons. So 26 and 33, I have a feeling this is going to be the one. 26 protons. So here's halfway, here's just over halfway. And 33, I would call that halfway right there. So 33 is like right about here. Yeah, look at this. So where our protons and neutrons interact. Oh, it won't let me zoom anymore. But you can see that that's just 1 unit away. This spot right here is just 1 unit away from that green spot. So if we have positron emission, right? We have positron emission, so we lost a positive thing. So this will go back 1. But will this actually work? Let's find out. This doesn't actually quite work the way I was hoping. We need to gain it. Now if we just go back 1, we're still not at that, unless this should have been lower. Well, I'm going with its iron still. Although now, okay, actually now I'm going to get meticulous. Let's actually count it and try to get accurate with this. Clear out some of this extra junk that I've added into here. So unambiguously, right here is 20. Like here's, let's zoom in as much as possible. We have 0 protons, 1 proton, 2 protons, 3 protons, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Oh, so 22 has several different stable options. Apparently 23, 24, so that's 24, and here is 25. So that is correctly lined up. If it was 26, there we go. So 26 is right on this line, and 25 is in between. And I really am just counting by mouth here. So if it's 26 and 33, let's see here, we have 1, 2, 3. Actually, that's balanced. So actually, I guess the answer, and maybe it undergoes multiple emissions. I am now saying that I think iron 59 looks great. That's not non-decay. So maybe I was just a little off my manganese assessment. Let me check that out again. But I think the answer is definitely manganese because it's radioactive. And manganese is 25, which is already where we are. No, that's 26, sorry. 25 is right here. 25 and 26 is what we're looking for. So here's our 20, 21, 22, 23, 24, 25, 26. And so if it had a positron emission, here's what it could do, is multiple positron emission. You lose 1, 2, if you lost 3 positrons, then you're on the line of stability. So that's my answer. I don't know if that's what the book would say, but I do feel confident saying that in this case, the answer is not chromium or iron 59 because those are not going to decay because those were both on the line. Manganese, I think, is going to lose 3 positrons. And that would take it from 25 down to 22, which would make it into an isotope of titanium. I buy it. Okay, nice. We are closing in. So these ones are all not in the band of stability. So actually, yeah, this is a good opportunity for us to clarify that vocab thing that I was a little blurred around. So 15, phosphorus 34. So it's at 15, what makes it phosphorus. Oops, so that's 10, 11, 12, 13, 14, 15. Phosphorus 34. 19. We're going to have 19. Here's 20. So here's 19. Oh, it just skips it. There we go. So there, let's refine it. What I said at the beginning of the video is incorrect. The band of stability is specifically the non-radioactive stuff. The radioactive stuff is existent, but not in the band. So I think I said that incorrectly before. I apologize. So we're talking this thing right here, which look, there's this gap. So basically, it could solve this problem by, well, we're doing decay, so it's going to send something off. So if it's number of, if it lost a neutron, I think its atomic number needs to go up one. If its atomic number goes up and its number of neutrons goes down, can we do that though? Can't really do that. So we're right there. So what if we go the other direction? Well, okay, so we're at 15. What if we did alpha emission? If we lose 4 from right here, so we go from 19, and then we're going to go 19, we're at 19, 17, 16, 15. There we go. Now we're on that blue line. We also lose 2, so we lose 1, because we're at, that's 15 right there. 16, 7. Oh, did we miss it that way? Jeez, this one's interesting. Let me come back to this one. Hey, let me see if any of these other ones are easier. And you know, while I'm at it, let's just copy the whole band of stability over here. Okay. So we have, and we're going to start out with, yeah, let's go for uranium. Hopefully this one will be more obvious. So 92. So first off, we're starting out with 92. So here's 90. 90. That's 91. 92. There's our 92. And 147 neutrons. 92 protons. So 150 is right here. 150, and we're looking for 147. So 150, 149, 148, 147. So it's this and this. It's like right here. This is what we're talking about. Oh, maybe I missed. And you know what? By the way, as a shape, you could be thinner. Make you look like that. Okay. So there, and this one. Same deal. Make you thin. And Sorry, this particular moment is a little wonky. There we go. Okay, so that is the uranium-92. And how is it going to get to something stable? Well, I think one good way to do that might be, in this case, I'm very inclined to say that it's going to have, here's our types of decay we can have. Not this table, but this one. Alpha, beta, gamma, positron, or electron capture. So I think we're going to have multiple alpha decays, probably, to get us to something on that blue line. So like, what if we could become bismuth here? In this case, well, yeah, I think it would be a combination of alpha and beta decays that would get us something more stable. And that is what uranium does. Right, so for uranium-239, first it would lose an alpha particle, and it'd become 235 and 90. 90 being, we just went from uranium to thorium. Yeah. And then the thorium is going to lose a beta particle. That's minus a negative, and therefore become minus a negative, becomes a positive, and it's going to go back and forth like that. So now, protactinum. Cool. And now it's protactinum. And it's going to keep going like that until it ends up on bismuth. So it'll lose an alpha and then it'll lose a beta. So this number went from 92 to 90, then to 91. And as it does it, it'll also slowly lose its total mass. So that's my guess for how uranium would degrade. How about for calcium? So 20 and 38 is way up here. So how is it going to get down to there? It could just like lose a bunch of neutrons, could be good. But if it lost, let's see here. If we lost one alpha particle, then we would be at 34, 18. We lost another alpha particle, we'd be at 30 and 16. This is starting to get more reasonable because now we're at 16s like here. Oh, I'm sorry, I super messed that up earlier because that would actually be 18 neutrons. So sorry, forget my logic there. It wasn't way up here. I was being a silly person who's at the end of a stream and got incorrect for a sec. So we're starting out with that. 20 protons and 18 neutrons. We're at 20 and 18's down here. So we basically want to gain neutrons or lose charge on our protons. So what I think we're going to get is this. We're going to get positron. No, we're going to get electron capture. Yeah, let's do that. Electron capture. We decrease our Z by 1. We have our thing, and it's plus an electron. And it's, wait. Y minus 1, Y. Huh. Kind of strangely written. But yeah, I think this is going to be electron capture. Let's try that. Because otherwise, if we have the electron comes in, then we end up with 18, 19. That's still not very good, huh? So it's positron emission then. So let's say, yeah, let's say it's positron emission. So we lose a positron, And that means that we have 18 and 19. Closer. We're almost there. So what if we just did that twice? We lose 2 positrons. Then we're at 18 and 18. And then we're right there. And we are argon, and we like it. So that's what I think is going to happen to that one. Ooh, so how about for tritium? We have 1 and 3. So that's like 1 and like 3. So that would clearly, is it clear? I don't know. I feel like it's just got to lose 2 neutrons, basically, right? But also, it could gain a proton. That's interesting, because if it, yeah, this is what I actually think. Can it gain a proton? Is that allowed? If it gained a proton, it becomes an alpha particle. But I don't think that's actually allowed. So never mind on that. So this must therefore be beta decay. Let's try beta decay. So if it loses an electron, minus a negative, now it is, if that's an E like that, so it's beta decay, it lost an electron, and now it's helium 3, which let's see if that's stable. It's not an alpha particle. We've got, so 0, 1, 2, got 0, 1, 0, 1, 2, 3. I think that is a stable isotope, so that's what's going to happen. See, helium can be 2, 2, which is the bottom of this vertical, or 2, 3. So that's what's going to happen, beta decay. And then we have this last one, and then maybe I'll come back for phosphorus. Maybe it's multiple alpha decays? That could be. I'll still do phosphorus on this video. Let's just do it. Okay, so phosphorus. Oh no, we're gonna do Pu first though. Is that plutonium? Pu is plutonium. 94. Plutonium 94. 90 for 94 is gonna be right about here. And then 2, that's gonna be 1, 1, 5, 1. 151. 151. So we're talking like right about here. So again, with plutonium, I'm just thinking it's going to be a series of alpha decay, and then beta decay, and then alpha, etc., until it finds somewhere stable. And that could be worked through. Maybe if I ever make an extra video on this, I'll do that. But let's just end with this phosphorus 34 one. So once again, phosphorus 34 must have 15 plus 4, so yeah, 19 neutrons. 15. So 19, and we've got 10. Got 10, 11, 12, 13, 14. Here's 15, 20, and 19's right there, once again. So how do we get this to be something more viable? Lose a bunch of neutrons. We lose an alpha particle from here. Then we lose 4 of these. So this would become straight up 15, which is 10, 11, 12, 13, 14, 15. And we'd be on 13. So 10, 11, 12, 13. So we're still not quite there with 1 alpha particle. That would get us from there to there. If we lose another alpha particle, perhaps. So neutron-wise, we're 1, 2, 3, 4. And proton-wise, we're at 1, 2. So yeah, that brings us to there. So that's what I think we're going to get, this double with this phosphorus. You're going to lose an alpha, which again is a 4 and a 2. You're going to lose an alpha, which gets you to 30 and 13. And that's elements, is that neon? Or aluminum? I mean, I should have known that. So that gets us to aluminum 17, it looks like. And that's going to decay into another alpha, which makes this now 26 and 11. And that is sodium. Now it's an isotope of sodium, sodium 15, which is on, we've got 10, 11. Oh, maybe that's 12. So maybe that doesn't quite get us there yet. Then we'd have to also have a beta emission, or maybe and a positron. There you go. I think we also need to then lose a positron. No, lose a beta. That's right. Then we're going to lose a beta, and that's going to bring us to that, which is sodium. That must be magnesium. And that is right there. Okay, so that's what I think will happen to the phosphorus, is it will become magnesium 16. Or sorry, magnesium 26. Okay, cool. If you watched the whole thing, thanks for watching that. This is actually the first time I've done the entire worksheet, I think, so that's pretty cool. Oh yeah, by the way, with that uranium, this is basically what would happen, right? So I started doing this, but that is a series of alpha where it loses the 4 and the 2. So that's cool. Look in your book for that, figure 21.9. And I guess we didn't do any half-life questions in this one. I thought we would, but we apparently didn't. And there's other stuff we didn't look at. So, and here's, yeah, look at all this stuff. This is in your book too. It's so handy. Figure 21.4 explains all this. Cool. Awesome. Thanks for watching, and good studies to you.